In this video, I want to discuss the idea of independent events. We say two events A and B are independent if the knowledge that A occurred does not change the probability of B occurring. In other words, the probability of B given A is just the probability of B. In this case, we have that the probability of A intersect B is given by the probability of A times the probability of B. As an example, a die is rolled twice. We're going to let A be the event. The outcome of the first roll is even. B, the outcome of the second roll is a 1 or a 3. Are the events A and B independent? And the answer is yes. What happened on the first roll has zero effect on the second roll. So these would be independent events. Next, two electronic components are selected from the production line for thorough inspection. It is known that 90% of the components have no defects. So I want to find the probability that the two inspected components have no defects. So probability of no defects in both of them. Well, the probability that the first one does not have a defect is 0.9. And these are independent. If one is defective, it has zero effect on the next one. So the probability that the second one has no defect is 0.9. So total, the probability that neither have any defects is 0.81. Next, a card is drawn at random from an ordinary deck of 52 cards. We're going to let A and B denote the events that the card is a 5 and the card is a spade, respectively. Are the events independent? Well, if we're not sure here, what we really need to check is the probability of A intersect B and the probability of A times the probability of B. If these are equal, they're independent, and if they're not equal, they're dependent. So let's think of the probability of A intersect B. A says the card is a 5 and B says the card is a spade. There is one card out of 52 that is both a 5 and a spade. Over here, there are 4 out of 52 cards that are a 5. There are 13 out of 52 cards that are a spade. And we can see these are not equal. So these would not be independent. Next, a laundromat's aging washing machine and clothes dryer are being replaced. The probability a new washing machine will require warranty service is 0.22. The corresponding probability for a new dryer is 0.15. So what is the probability that both will require warranty service? Well, the chance for a washing machine is 0.22 and it is independent from the dryer. The probability that this happening has zero effect on the probability of the dryer. So I would multiply by the probability of the dryer, 0.15. And this would give me 0.033. And I want to start to consider 3 events and see how that works. Our default may be to say that the probability of A intersect B intersect C is equal to the probability of A, probability of B, probability of C. But let's look at that a little bit closer. So we're going to roll a die once and record the outcome. We're going to let A be the event 1, 2, 3, B be the event 3, 4, 5, and C be the event 1, 2, 3, 4. Now I want to verify that this is true. So the probability of A intersect B intersect C. The only thing that all 3 of these have in common is a 3, so this would be 1 over 6. Probability of A times the probability of B times the probability of C. Well, the probability of A is 1/2. The probability of B is 1/2. And the probability of C is 2/3. So when I multiply this, I get 2 over 12 or 1 over 6. So this is true. However, the probability of A intersect B, still the only thing they have in common is a 3, so that would be 1 over 6. However, the probability of A times the probability of B would be 1/2 times 1/2, which is 1/4. So even though this works to have that the probability of the intersection is the multiplication of each of the probabilities, these are not independent. So how do we define the independence of three events? Well, we need a few things. First, we do need that the probability of A intersect B intersect C is equal to the probability of A, probability of B, probability of C. We also need that the probability of A intersect B is equal to the probability of A times the probability of B. We need the probability of B intersect C to be equal to the probability of B times the probability of C. And finally, we need the probability of A intersect C to be equal to the probability of A times the probability of C. So we need all of our events to be pairwise independent. So let's look at some examples of bigger situations. At 25 degrees Celsius, 20% of a certain type of laser diodes have efficiency below 0.3 milliwatts per milliamp. For 5 diodes selected by simple random sampling from a large population of such diodes, I want to find the probability that all 5 will have an efficiency above 0.3 at 25 degrees Celsius. Well, the chance that the first one will have efficiency above 0.3 is 0.8. Since there's a 20% chance it has efficiency below 0.3, there must be an 80% chance that it has efficiency above 0.3. The same is true for the second, the third, the fourth, and the fifth. This gives us a total probability of 0.32768. Next, what's the probability that only the second diode has efficiency above 0.3? So the first one will be below, the second one above, third is below, fourth is below, and the fifth is below. This would give us a probability of 0.00128. So this is the probability that only the second diode has efficiency above 0.3. What about the probability that exactly one of the 5 diodes has efficiency above 0.3? Well, it could be the first, and then I have the next 4 that are below. It could be the second, and the rest are below. It could be the third is above 0.3, the rest are below, etc. So we have to consider 5 different possibilities here. So what we're looking at, each one of these has a single 0.8, the one that's above, and 4 0.2s, the 4 that are below. And out of a total of 5, I need to pick 1 to be above. So this 5 choose 1 accounts for how many different possible outcomes we have here. So the total would be 0.0064. So if we want to consider only 1, we need to consider where that 1 occurs. And we typically use a counting argument to help us figure that out and figure out how many possibilities we have. This time, we want the probability that exactly 2 of the 5 diodes have efficiency above 0.3. So 2 of them need to be above 0.3, which has a probability of 0.8. 3 of them need to be below, which has a probability of 0.2. And we need to determine where these 2 that are above occur. Do they occur in the first and second spot, the first and third, the second and fifth, etc.? So to figure out how many different ways we can arrange this, we have a total of 5, and we need to pick where 2 of them occur, these 2 that are above. And if we work this out, we get 0.0512.